And now we're in a completely flip scenario where battery prices are at the lowest they've ever been, down at $50, $60, $70 a kilowatt hour, and the lithium price is back down at kind of $15 a kg. The improvements we've seen so far have been either more material in the same volume or just physically larger cells being able to hold more material.
When we look 5 years in the future, where do you think that might get to? Is there kind of a natural floor to that where we'll kind of not get below? What does that curve look like and where could we get to?
If you do things like optimize the performance of the cell, get as cheap raw materials as maybe as possible, and then do things in the factory, and then as we go on to this kind of next generation or newer technologies, I think there's definitely scope for the cell costs at least to fall below that.
Understanding the factors driving cost reductions in battery cells is crucial for staying competitive. But material costs are not the only thing influencing prices. Breakthroughs in cell chemistry, system efficiency, and manufacturing practices all play a role in determining the price. In this week's episode, Aaron Wade, head of battery costs at CRU Group, joins Ed Porter to explore the latest in supply chain insights and cost projections and what they mean for the future of energy storage. If you're enjoying the podcast, please hit subscribe so you never miss an episode, and leave us a rating wherever you listen. Let's jump in.
Hello and welcome to another episode of Transmission. Today we're joined by Aaron Wade from CRU. Aaron, welcome.
Thanks, it's great to be here.
And I'd love just to get started by getting a little bit on your background. So who are you, who are CRU, and what do you typically do in the battery space?
Sure, so I am a chemical engineer, studied at UCL just down the road, and then I did a PhD in battery degradation. So I was using X-ray imaging to look at when and why battery materials failed and how we could design both them and the X-ray machines better to optimize the imaging process and the battery performance. And then while I was working on my PhD, I started working part-time for a company called XWatt. So they were based up in Sheffield in the north of England, and we did techno-economic analysis of batteries, solar panels, and power electronics. So this was figuring out where the technology was going and how much it could cost. And then about a year and a half ago, a company called CRU bought XWatt. So I came over as part of that acquisition, and now I lead the battery cost modeling work that we do at CRU. So CRU has a 50-year history of forecasting metals, fertilizers, looking at the cost and emissions from mines and forecasting out supply-demand balances and that kind of thing.
Okay. And who typically reads your reports on battery costs?
So I'm quite fortunate to work in a space where the research I do is very interesting for a wide range of people. So I can give you an example. So if someone's making, let's say, some new cathode materials with elevated performance, it's interesting to know how good that is on an isolated basis. But what's more important is to understand how it might cost or what the cost profile of a cell that it's in might be. So we work with people designing materials or buying cells or making factories, that kind of thing, to see where the cost to manufacture these batteries might go. And then we also work with people investing in the space. So either investing in these companies or investing in gigafactories. So it's really quite a broad range of people that we work with.
Okay. And to kind of, I think, start off with the juiciest parts. So I'd really like to get into battery costs straight away, because I think a lot of people listening to this podcast will be battery owners, financiers, people interested in the space. So could you just talk a little bit around what's happened over battery costs in the last few years, and then let's go from there into what the future might look like?
Sure. So I guess the most interesting point of the last few years was back in 2022 when the lithium price was really, really, really high. So 2020, 2021, it was about $10 a kilogram, went all the way up to $70 or $80 a kilogram. So this caused the cost to produce batteries, and therefore the price that they were sold at, to be jumped up very, very quickly up to kind of $120, $130 a kilowatt hour. And now what we've seen is as the lithium prices come down, the cost to produce has come down. And now we're in a completely flip scenario where battery prices are at the lowest they've ever been, down at $50, $60, $70 a kilowatt hour, and the lithium price is back down at kind of $15 a kg. So we've seen this kind of massive jump in prices and then this fall until the present day where we are now.
Okay. And that's lithium carbonate?
So yeah, the lithium we use is lithium carbonate or lithium hydroxide, depending what chemistry we have on the cathode side of the cell.
And that in 2022, you said jumped almost 7x to get to that kind of $70 to $80 range. What were the drivers behind creating that price hike?
So I think fears of shortages of supply was a big reason. The margins that people were making when selling this were really big, and there was just an expectation that there'd be a shortage of material, and the prices kind of tumbled further and further up. And then now more suppliers come online, and then we're seeing that the prices come all the way back down.
The kind of classic adage, right? High prices cure high prices. And so those lithium prices are now back down around $10, you were saying. And that has brought battery costs down to the range of, say, $50 to $70 per kilowatt hour. And by per kilowatt hour, you mean kilowatt hour of capacity in the battery cell.
Yes, we measure the cost of a battery in dollars per kilowatt hour, which is essentially how much does it cost to store 1 kilowatt hour of energy in the cell.
Okay. And then it feels like there's kind of highlighted there like quite a strong link between the lithium price and the battery cell cost. Is that fair to say that we should be looking to lithium as being like this primary driver of what influences battery costs? Or is it kind of a smaller part of a wider mix?
So material pricing and materials make up the biggest component of the cathode, well, of the cell cost, actually. So in a cell cost, the cathode might be 40 to 50%, up to 60% of the total cell cost. And then of that, lithium can be kind of 30 to 60% of the cathode cost. So as a single component, lithium and then the cathode is the biggest cost driver. And then we have other materials like the graphite in the anode, which is significant in the cost structure as well. But lithium is I would say, the single biggest cost driver in terms of likelihood fluctuation and biggest impact.
And so as a percentage of the total cell costs, like what would we allocate to lithium?
So kind of between 20 to 30 to 40%, depending on the type of cell.
Okay. I think that'd be quite useful for people because I think often people look a lot to kind of like lithium prices and say, well, if that doubles, what does that mean for my cell costs? And maybe that kind of highlights a little bit of the cost reduction we've seen. So coming down from 2022 highs to where we see pricing today, because that hasn't all come from a reduction in lithium. So what's kind of driven that cost reduction in cells?
Yeah, so I guess there's essentially two eras that we could consider. One is the cost reduction era, and then one might be the performance improvement era. So the cost reduction era is typified by the cost falling because economies of scale have been reached. The lithium price may come down, so you're kind of maximizing the amount of bang you get for your buck, so the cheapest raw material pricing. But now we're kind of in this performance era because prices are so low. So we can see innovations at the cell level, innovations at the pack or system level, and then innovations within manufacturing. And all of these three can come together to reduce the amount of material we might need in the cell, but also reduce kind of the other costs of manufacturing, which is why we're still seeing the price come down, even though the lithium price is somewhat more stable now.
Okay, so you're saying the same amount of lithium goes into that cell, but the cell can work at 110 or 120% of what its predecessor could have done.
Yeah, so we're seeing, so one example is cells are both getting bigger and storing more energy for the same volume. So the standard cell in stationary storage used to be a 200 something amp hour cell. We're now seeing the physical same size cell be able to store over 300 amp hours, so 314 amp hours. So this cell does have a little bit more material, but it has less wasted things, like the ratio of packaging to active material has gone down. So then you get kind of incremental improvements in cell cost through that. And then we're also seeing, so EVE announced today, they're starting production of their 600 amp hour cell. So these are huge cells, again, more efficient. And then this can be one of the reasons why the cell costs may keep coming down.
Okay. And is that, when you say 600 amp hours, are you kind of increasing the volume of that cell and therefore it becomes a 600 amp hour? Or are you kind of saying the cell size and material remains the same and this is purely just improvements in the performance?
So the improvements we've seen so far have been either more material in the same volume or just physically larger cells being able to hold more material. But there's also another stream of innovation, which is where you can eke more performance out of the same material. So this can be by changing some of the chemical composition or expanding the performance of the cell.
Okay, well, maybe let's talk about the changing chemical composition then, because this has changed quite a lot. So where were we back 2 years ago?
So I guess the conventional wisdom, at least in the Western market, was that NMC, so nickel manganese cobalt oxide, was going to be the cell or the chemistry of choice. This was because at the cell level, it has a greater energy density. So you can, for the same mass, store more energy. So obviously for a vehicle, that's really helpful because your car may be able to drive further. But then even for stationary storage applications, you might be land constrained or weight constrained, and you want to maximize your kind of floor space.
And so in a lot of sort of consumer electronics today, NMC still is the choice.
So we mainly have something called LCO, which is just cobalt oxide essentially. So that's the main choice for consumer electronics. But what we saw was a big shift towards LFP a couple of years ago. One of the big drivers for this was something called cell to pack innovation. So both in vehicles and in systems, the traditional way of packaging up a cell is you have a cell, then you have a module, and then you have a pack. And then between all the layers, you might have some safety, thermal suppression, but you also had these rigid structures that could kind of take the load. But a company, BYD in China, kind of were the first to market with this cell to pack concept where you didn't need the modules and the cells could somewhat become structural components of the pack. And what this enabled the LFP cells to do was at the pack level have energy density similar to some of the NMC varieties. So now BYD, and in fact most of the Chinese market, is LFP, and they have supercars that use LFP rather than what the conventional wisdom is on the NMC side. And LFP gives now acceptable energy density, so acceptable range, but it's cheaper materials, so therefore the cell cost is lower.
Okay. And I think we've seen that or come through a lot of the stationary storage as well in terms of the types of cell chemistries we see. Maybe the really interesting part of this is where does it go in the future? So it's still, to some degree, lithium is quite tricky because to some element, it's not a nascent technology. It's been around for a very long time. But as scales come through, as does innovation, and so we see even within the last 2 years, the move from NMC to LFP, some of the innovation around pack design and how much more you can get into a particular cell and how much longer that can run for. It feels like in lots of ways, the tech is getting better. Where could this get to? So if we were to put the kind of crystal ball out and say in 5 years, where do we think this could get to? Are we thinking LFP will be off the table in 5 years and there'll be something else that sits there and becomes the dominant chemistry or composition of choice? What do you think?
So I think the first key is different markets are going to have different chemistry choices. And then within that, there'll be sub-markets. So if we look at the EV market, we have a whole range of class of vehicle, from your kind of cheaper vehicles with lower range all the way up to your super high performance. And it's likely that LFP will take a big chunk of this market, but NMC is likely to still have its place within it. But then we're seeing innovation both on LFP and within NMC. So on the LFP side, there's the addition of manganese to make it LMFP, which essentially enables you to go to a higher voltage, so then your cell can have more energy in it. But there's big issues with cycle life that still haven't been solved. So this is actively being researched, and actually LMFP is often now mixed with NMC to kind of get it into the real world and get some data so that the performance can improve. And then on the NMC side, traditionally we would increase the nickel ratio and reduce the cobalt ratio. So we'd have something called, we started with 111, which was equal ratios of nickel, manganese, and cobalt. Then we moved to 622, which was 60% nickel, 20% manganese, 20% cobalt. And then now we're moving towards 811, which is 80% nickel. But interestingly, a lot of the Korean companies are going back down to 622, but operating the cell at a higher voltage. So this, again, saves a little bit of cost because cobalt is quite expensive. So if you can reduce it, you get some benefits. So they'll go to like 613 with 10% cobalt, and you get some performance boost because you go to the high voltage. So all of that to say is there's lots of innovation going on at the material level, which means that at the minute LFP is dominating, but there's definitely room for kind of all chemistries to compete in the space.
It's not like NMC are done and we'll never see NMC again.
Yeah.
It feels like there's kind of continuing strands of work on all of this. And maybe to add one more into the mix, so sodium ion gets talked about a lot. Is that justified conversation? Is that something that we'll see coming into stationary storage, or is it kind of too early to say?
So I guess sodium ion was really at the kind of peak of its hype in 2022, 2023, when these lithium prices were so high. We had lots of people working on it, but also lots of companies putting out announcements about how soon they were going to produce these cells. And as the lithium prices come down and as the LFP prices has come down too, the sodium ion hype has kind of faded away. The cells are still more expensive to produce than LFP cells and are worse on both an energy density and a cycle life perspective. So there's still some kind of performance improvements to be had and reduction of the cost of the anode, which is the limiting factor in terms of. But then we also see hesitancy in the market to adopt a new technology. If you're financing an ESS farm
Yeah.
and you're spending millions and millions of dollars, are you going to go with the technology that's been around for years and has been proven and is bankable and insurable, or would you take a risk on the newer tech? So speaking to some people is we'll let other people take that risk, get some field data, and then when the anode cost comes down and the cells are competitive and we see how they perform, there might be the transition. But I think I like sodium ion for two real reasons, which is one, if people have the option to swap over, it means that lithium prices can't go super high again because people have that substitution option of going from LFP over to sodium ion. And the second is supply chain security, which is if you want to buy cells today, the Chinese market really dominates and the Chinese companies really dominate all the way back from mining all the way to production. Mm-hmm. Whereas because sodium ion is a newer technology, there's some more space for people to operate. And then if they want to produce kind of locally grown cells or have kind of a footprint in the market, there's more of an option to do so on the sodium ion side.
Okay. Well, let's come back to the supply chain and manufacturing piece in a second, because I think also some interesting anecdotes from your recent trip to Chinese manufacturers would also be good to cover. But I think just before we go there, let's just round off the cost piece when we look 5 years in the future, pounds per kilowatt or pounds per kilowatt hour, sorry. Where do you think that might get to? Is there kind of a natural floor to that where we'll kind of not get below, or do you think that there's kind of diminishing? Like, what does that curve look like, and where could we get to?
Yeah, so I did some research looking at how low could LFP costs get to realistically in the next couple of years. So if you do things like optimize the performance of the cell, get as cheap raw materials as maybe as possible, and then do things in the factory to reduce workers, increase the line speed, that kind of thing. We ended up at $25 per kilowatt hour at the cell level, being maybe ambitious, but not completely unreasonable. So these are all innovations that seemingly could happen. But then that's just with the established technology of a certain size. And then as we go on to this kind of next generation or newer technologies, I think there's definitely scope for the cell costs at least to fall below that.
Okay. And it's kind of like a really remarkable number, right? So at £25 per kilowatt hour, the actual cost of adding extra capacity to your battery sites is incredibly low. And so when we start to say, oh, well, will it be a 4-hour system? Will it be a 6-hour system? There is more to just batteries than just a cell cost. But if you are literally adding that at £25 per kilowatt hour, the ease with which lithium chemistries could go to 6, 8, 10 hours really does feel like that's a massive enabler. Perhaps you could just talk a little bit about how the cost of cells stacks up to getting to like a 20-foot container that we might see at one of like the battery sites that exists in the UK or in the US. So how do you get from a $50, let's say $50 cell, to a 400K per megawatt hour battery system?
Yeah, so I mean, I agree that we're in an exciting phase where as cell costs keep coming down, everything gets cheaper, and then there's more opportunities. And we're already seeing this in the market with longer and longer duration of battery storage going in. So if we think about the cell, the first option, the cell at $50 a kilowatt hour, we then put that in a pack. So then there's some additional casing, some cabling, some cooling, that kind of thing. And then we stack those into a system with kind of a cabinet door and some more metal. And then that goes inside kind of a bigger system that might have an HVAC or have an inverter. It'll have some fire suppression, and it'll have obviously all the containerized metal for the system. So typically at the minute, a cell is about 50% of those costs. But then obviously as the cell cost comes down, some of these may also decrease, but it's unlikely that the cost of inverter will come down alongside it. Same with kind of the fire suppression and those kind of things. So I guess on one avenue, you're still going to need all of those things. But then what we're seeing is because people are getting more confident, the energy density of these systems is going up. So we used to see kind of a 1 or 2 megawatt hour system. Now we're seeing pretty much 6 as becoming the standard.
You're saying, 1 or 2 megawatt hour system per 20-foot shipping container?
Yes.
Yeah. Okay.
Yeah, and now we're seeing much greater energy density. So this is enabled somewhat by the cell to pack, but then all of your fixed costs in your shipping container remain pretty much the same. But if you're putting more energy into it, your total cost is also still going to decline. So
the cost of the iron in the shipping container remains, or the steel remains the same, but because you're getting more energy into it, then that's how you decrease the cost.
Yeah, so then the dollars may stay the same, but because the kilowatt hour or megawatt hour is increasing, your dollars per kilowatt hour can keep decreasing. So we're likely to see decrease both at the cell and system level over the next couple of years.
Okay, interesting. I think there's something that is really topical at the moment, because certainly within the UK, we're looking at how do we start to address long duration storage? What might the future look like? We have some older technologies that have been around for a long time, things like pumped hydro, and we're really trying to work out, okay, how quickly will electrochemical solutions move to be competitive in the 6 to 8 to 10 hour range? And if it's £100 per additional hour of duration per megawatt hour, then it starts to tilt over quite quickly. But if it gets down to say 50, then all of a sudden, like that sort of tipping point between those techs happens much further out. So it's really, really, really topical, and not just in the UK, but also in the US as well. Perhaps let's come back to China. So a lot of the manufacturing and supply chain at the moment comes through China. Why is that?
Well, the first reason is because the Chinese government 20 years ago identified batteries and electric vehicles as an area where they wanted to compete and become kind of global leaders. And then from there, they set out a 5-year plan every 5 years to work out where does the technology need to get to, how much capacity do they need to have, all of these things. So it's something that the Chinese government and therefore the Chinese companies have been working on for a really long time. And there was lots of state support to help this. So land was very cheap, buildings were very cheap, maybe free, to help companies kind of get started and establish themselves. But then this was a time when the manufacturing efficiency was pretty low. So cell costs were still very high. And what we've seen over the past 20 years is that Chinese engineers have really optimized the production process of batteries. So now they can, the yield rates in the factories are 98, 99+%. So they're really, really efficient at making these cells.
Let's pause for a second on a yield rate. 98%, what does that mean?
So it's essentially how many cells, how much material you make that make it to the final battery cell. So we see startups in Europe and America and all over the world really typically operate at kind of 40-50% to get going, and then they ramp up and try and improve that over time. And it's really difficult to eke out even a single percent of your factory because there's so many processes that are going on and everything is related to everything else. So making a small change at the beginning of your production process is going to have a large change somewhere else, and then it's all kind of linked together. So the Chinese engineers who have optimized this solution can now fantastically make cells at really good yield rates. And then obviously the more material you buy that doesn't end up in your cell, the more your cell is going to have to cost to offset that.
Yeah, so it's almost like already you get a 2x hit on your cost of your system. Just to kind of give people a flavor, so those numbers feel wildly apart, right? 50% yield to 98% yield. What are the key factors in that?
So I think a lot of it is time, which is when there was no other competition. Even if you have a 50% yield loss, you can still sell at a market competitively because there's no one you're competing against. And then the more cells you build, so that the scale of manufacturing in China is huge, the more expertise you have, the more knowledge you have of the whole process. But then also, the Chinese industry is huge. You can buy recipes for cells. You can buy parts of the cell made for you that you just put into your system. So there's lots of kind of tricks that people can use to get going. But we see it's really the knowledge of people, I think, that have helped that. There was a new facility or a new company that wanted to make cells. I saw them a couple of months ago at a conference. And they started manufacturing in March at this kind of very low yield rate. And then by 3, 4, 5 months later, they were already up at the 90+%. And when you compare that to the Western companies who are trying to do this, it's taken them years and years, and we're not even close to that level yet. And the real answer was they hired a bunch of engineers who knew what they were doing from another company, came over. But I think that in itself is tricky because other companies have tried that. But if you're not doing the same technology with the same machines, with the same everything, it's not just as simple as hire the engineers. But the people, I think, are really important to the story.
Okay, and maybe on that, so yield and the quality of the cell, are they linked at all? Or is there kind of, if you're running a factory that's 50% yield, are you getting out the right quality of cell as a result of that? Or are all of your cells sort of a lower standard versus a 98% yield factory?
Yeah, so even the top different grades of cells.
Okay.
So you have A, B, C, maybe D, and they'll sell for different prices. And they'll
A being the best.
A being the best.
A being the best.
But they'll sell for different prices, and they'll also go into different applications. So a lower grade cell might not go into a vehicle, but it might go into a electric scooter or something like that. So even the top factories have this tolerance, and I guess part of the goal is to narrow the tolerance so you're making only A cells, especially if you're trying to sell to automotive companies. There's kind of fluctuations and variabilities on how big those gaps are and what's acceptable and what's not, depending.
And when I buy like a 20-foot shipping container, not that I've ever bought a 20-foot shipping container full of batteries, but if I ever did buy that, would it come on the side, would it say this is a B and they're all B cells? Or does it say this is like a weighted average B and there are some A's in here and there are some C's in here? How does that work?
So sadly, I've also never bought a shipping container. Maybe we should team up and buy one so we can see. But I think what companies will try and do is match the capacities of cells rather than just it's harder to predict the long-term performance, but knowing that your cells start at the same energy storage level, then you can discharge them all equally and they won't get some that are 50% discharged and some that are 100% discharged.
So you're looking for consistency within the overall like containerized BESS.
Yeah.
Okay. And so then it feels like the next question logically on China versus US or Europe is, with that type of difference in yield and with that type of difference in terms of supply chains and the ability to go and pick up another component from another factory and drop it into yours, it feels like almost there's no way to get back and to be comparable in terms of cost of cells. So where do you stand on the impact of the Inflation Reduction Act on bringing manufacturing into the US, but also into Europe?
It's a big question. So I think part of what we should be doing is collaborating across the world. I mean, fundamentally, everyone's aiming for the same thing, which is to enable a switch to this kind of cleaner electricity source. But naturally, countries want to protect their own manufacturing ability or jobs and all of these things. So at some level, subsidies and help are needed. But you're right, the difference between how the US and Europe are playing this is very interesting, with the US looking to essentially cut out Chinese and other supply chains. So we're seeing lots of joint ventures with car manufacturers and South Korean or Japanese companies working together to build cells, versus in Europe where we have some companies going alone, so Morrow or Northvolt, and then other areas where Chinese or Korean or even Japanese companies are coming over to build their factories. I was actually looking today at how much might it cost to just take a Chinese factory and replicate it in Europe, and could you sell at the same cost? And the production cost is higher because of higher electricity prices, kind of the main driver, but labor cost. But it will be a challenge for kind of these homegrown companies to then start to compete and sell, at least in the short term, against the Chinese companies that have been doing it for so long and have so much experience on the manufacturing side.
And is one element of this on the recycling element? So by having manufacturing and production within Europe, is there an element of the recycling programs that are being looked at? Will that influence the cost of manufacture, or are those two things kind of or separate?
The need for recycling is great, but I think the impact that requiring recycled content in the cell will have is probably minimal in the short term. There are really two key elements to this. The first is how much of a premium, if any, will recycled content have? And the second is how much of that material will you put in your cell, either to meet regulations or to have a cleaner, greener product. So on the first element, will there be a premium for recycled content? I think fundamentally it depends on, is there more demand or is there more supply, and what does that mean versus kind of conventional mined material? And I think that will be dictated by the fines or punishment you might receive if you don't include recycled material. If those fines are really significant, people will probably pay even more so for this recycled content than not. And then if we move on to the amount in a cell, so even with a 50% premium, if you meet the lithium required recycled content, it's only a couple of percent. So it's only going to add 2-3% to the cost of your cell. Whereas if you were going to go all the way and do 100% recycled lithium content in your LFP cathode, depending on the premium, you could be kind of 3-5% or up to 14% increase in cell production cost. So then it comes down to, will people pay more for a cell that has that recycled content in? And I think at the minute the answer is no, but maybe with time that'll be something that people will be interested more in, or maybe funds will kind of require that if you're going to invest in assets, do you need to be making sure that you have at least some percentage of recycled material in the cell?
Is there also kind of a world that we see where, almost from like a security of supply perspective, people look to bring more lithium recycling into European supply chains, and that is sort of to some degree like a way of offering much more security to that manufacturing process? Do you think that's likely to happen?
So I think if we look at what happened in the Chinese industry first, which was the initial recycling was set up around the gigafactories so that any of the scrap could be recycled and then turned back into the materials and then put back into the line. So I think that would be a good first step, which is, as these factories are set up, make sure that any of the material that comes off the line is then recycled back into the process, rather than maybe shredded and then sent to somewhere else in the world for the materials to be leached back out. But then over time, there's no reason why you can't have a fully localized supply chain. I guess the real issue is, when is there going to be enough volume of cells that can be recycled to actually account for that? And especially with LFP having a very long lifetime, and if more and more people are adopting LFP, that becomes 10, 15, 20 years down the road, rather than maybe 5 or 10 with the NMC cells that die a little bit quicker.
Is that one of the challenges on recycling in terms of NMC? Each of the components are quite valuable as standalone commodities. LFP less so, and then going into sodium ion even more, kind of even less valuable. And so the premium for doing that recycling kind of drops off. So it's almost like a bit of a weird kind of feedback loop, that as we move to these less valuable input materials, the recycling process will be less valuable for LFP.
Yeah, for sure. So we see, so recyclers will typically pay for NMC cells because they know they can turn the nickel and the cobalt into profit. Whereas on the LFP side, they might be paid to take those cells away because they have to factor that into their business model or revenue streams, as we need to receive some money because we're going to get less back for the recycling process, because, as you say, the material inputs for these cells are a little bit cheaper.
Okay. And is it still the setup, effectively, that the manufacturer of the cells have to take back the cells at end of life? So if you're a manufacturer of an NMC cell within Europe, you have to take back that cell?
Yes, I think
yes,
so. I think that was, I don't know how far along we are on that process, because there has not been swathes and swathes of material coming back.
It feels like we're in the extent to batteries ramping up from like 2010, where we had a couple of megawatts here and a couple of megawatts there. Mm-hmm. We have kind of gone through a bit of an S-curve on the amount of batteries now on the system. And so if you think recycling is kind of 10 years on from there, then the recycling will go through this kind of this S-curve and will become a much more topical part of like how the supply chain goes full circle. I think one interesting thing we saw from the Rocky Mountain Institute recently was a piece around the need for raw materials. And so at what point could you start to get all of the existing cells off the market, recycle them, and then through better manufacturing processes, as you've just been talking about, could you almost make like a closed loop of battery chemistries and not have to go and procure so much lithium from the market? Have you like, do you think that the logic of that is sound? Do you think that's possible?
I guess that's kind of the dream of why batteries and energy storage in general is kind of the future rather than combustion, because there is theoretically at least a world where everything comes full circle and you never need to mine. I think because EV adoption rates and also BESS installations are increasing, that's still quite a long way away, because I mean, we're so far from 100% renewable penetration or EV penetration or BESS adoption that it'll be quite some time before that happens, and then even longer until we can go full cycle. But I think it's definitely possible and hopefully will happen because of kind of losses in the system. I assume some mining will still need to take place, but there might be a world where it's much reduced.
It's almost made up because the production quality of the cells is better. Okay, interesting. I've got two questions to finish with, but perhaps before I go there, I just wanted to just to get your take on battery costs over the next few years. Coming back to that topic, now we've just talked about how cells are manufactured, what the manufacturing lines look like, how things like the Inflation Reduction Act will impact cell costs. What do you think the kind of the shocks might look like over the next 2 to 3 years? Should people be kind of penciling in $50 per kilowatt hour on their battery cell costs in business cases? Or do you think that actually it's going to be $50, like, but maybe plus or minus some shocks on the horizon? Do you see kind of scope for those shocks to hit battery costs?
So we don't think raw material prices will significantly increase over the period. So, I mean, there's always some level of uncertainty with commodity markets. With those being relatively stable and kind of incremental improvements, at least on the Chinese side, for reducing the number of workers, increasing the yield slightly, increasing the throughput of the machines, it's likely we'll see incremental reductions, at least for the top companies in terms of production cost. What I think could be interesting is right now we're seeing only a few companies in China making any money, with the vast majority selling at cost or below cost. So there's likely to be kind of a big consolidation period where the major manufacturers buy some of the smaller ones, or they go out of business and kind of die out. So I don't know if that will have a massive shock to the pricing, but there's a world where a lot of companies go bust and then maybe CAT will buy them and then can produce even cheaper because they got all of these kind of battery factories for £0, so they don't have to pay any depreciation on it. But I think for the most part, the costs should continue to kind of come down.
And there's also an interesting thing around the manufacturing capability and the actual demand for these. And given year on year, the quality of the cell gets better. If I'm a manufacturer and I have an oversupply, let's say 100 gigawatt hours, I really do not want to be sitting on that year to year, because the stuff that is coming is going to be better tech. But also I'm seeing degradation on those cells once I've manufactured them. So I kind of need to get rid of them. So it feels like the actual supply chain of the system is quite set up to be oversupplied, and you can have quite a big drop if that manufacturing is kind of outpacing demand.
Yeah, so we're in a massive scenario now where there's far too much capacity kind of throughout the supply chain. So everywhere from lithium mining to cathode production to cell production. This is part of the reason why cell prices are so low, because there's just this massive overcapacity. So factories are running at low utilization rates, so the machines aren't running at kind of max speed, at least for the smaller manufacturers. So the overcapacity is likely causing this big drop.
Yeah, and I think maybe the other way that I think is quite interesting is, like, if the overcapacity is causing the drop, then like you could foreseeably see a world where that flips the other way, right?
I think the way the market, especially in the Chinese industry, which dominates, is set up, it's unlikely there'll be undersupply.
Okay.
Because, I mean, we're almost at double the amount of LFP manufacturing than we would need to fulfill. So there's just so much overcapacity, but still people are building facilities with that long-term view of demand for these cells is going to increase. And if we have a brand name and we're established, we can sell both within China, but kind of to the rest of the world. So I think overcapacity is definitely here for a while. I mean, a good parallel is the solar industry, which is also in a massive state of overcapacity, and module prices have kind of hit rock bottom. But we don't think that's going to go away pretty quickly, and we think maybe that will extend over the next couple of years. So I think
until a better tech comes along to fundamentally replace the need for that thing, there is still this kind of concept that tomorrow's demand will be bigger, and if you kind of want to get on that boat, you kind of have to get ahead of it.
Yeah.
And that's kind of what's driving this kind of systemic oversupply, even though like low prices should cure low prices.
Yeah, and I guess also depending on what the next step is, if it's a slight change in chemistry or a slight form factor increase, you can probably make that with your existing line. So if you're agile enough to make new chemistries as they come up, then even having this oversupply isn't going to kill you, because you can just kind of slightly pivot rather than completely change to a new manufacturing method.
Okay, fascinating. I have 2 more questions for you. First one is there anything that you would like to plug?
Yes, I'm part of something called the Volta Foundation, which is a non-profit trade organization that is for people in the battery space who want to learn, network, collaborate. So we hold online and in-person events all over the world. So if you want to join kind of the largest battery network and largest network of battery professionals, look us up, because we do events everywhere, and it'd be great to have people join us.
You had one in London very recently?
Yeah, I had one last week. I have one in Oxford in a few weeks as well. So we kind of travel around the UK, and we have some in Boston coming up as well. So it's global events.
Very good. A perfect thing to plug. And do you have a contrarian view? Do you have something that you believe that the majority of the market doesn't?
I think I have 2.
Okay. Yeah, we have time for 2.
Okay, so the first one is a lot of companies say they want to buy locally sourced batteries, but they're only going to buy them when they're cost competitive. So for now, they'll buy from China. And some part of me thinks that by continuing to do that, it means the locally sourced cells won't have anyone to buy their batteries, won't have any revenue, will continue to struggle. And we may be in a world where we actually have none of these companies being able to produce, because they start to go kind of bankrupt, as we've seen Northvolt's having trouble. And as soon as somebody makes another choice, your whole production is kind of in trouble. So that's the first one. And then the second one is that I think especially the Western industry should really focus on the manufacturability and just getting production of cells out there. I think there's a lot of interest on kind of next gen technologies, whether it's lithium sulfur or solid state or even recycling, but without focusing on manufacturing kind of the basics, as it were. So kind of LFP or standard NMC cells, we're going to struggle to produce anything. And then the Chinese companies who already are and are innovating will dominate. And then the Western companies will really struggle.
It's almost like if you want something done, you should ask a busy person.
I've not heard that, but yeah.
Yeah, okay. Aaron, thank you very much for coming on the podcast. You've been a brilliant guest, highlighting some of the intricacies of the supply chain, where it might all go in the future. And yeah, thank you very much.
Thanks for having me. It's been great.
Thank you for listening to Transmission, a Modo Energy podcast. Transmission delivers conversations from industry leaders and experts exploring energy markets and the operations and technologies related to grid-scale battery energy storage. Check out our other episodes by searching Transmission wherever you get your podcasts. Check out the Energy Academy, our video crash course on how markets in Great Britain and ERCOT work, or head to modoenergy.com to see our written research. Thanks for listening.